All right, well, y'all doing good? Yeah? All right, in terms of where we are in the class, I was looking at this morning. We are not going to have another exam before the drop date, which is on the 15th, I think next week. So our next exam is scheduled for after Thanksgiving. Hey, you doing all right? Good. I thought you weren't feeling well last week. You all right? Weren't you saying you were feeling sick?
Oh, yeah.
Yeah?
Yeah.
You're all right? Oh, ooh. Okay, so what do y'all think about an exam after Thanksgiving?
I'm going to be out of town. I don't care.
After Thanksgiving?
Yeah, the week after. I guess
Yeah, I mean, we can try and...
I say we do it before, just to get it like over.
If we do it before, it'll be on the 23rd, I think. Yeah, is that right? No, sorry, that's Thanksgiving holiday. It'd be the 21st. The 21st, which would be 2 weeks from today.
I'm down. Yeah.
What do y'all think? Let's do like an informal vote real quick. How many of you think you'd want to have it 2 weeks from today? That would be before Thanksgiving. Okay.
Wait,
How many?
Tuesday?
It would be a Tuesday. And then how many of you want to do it after, right when we come back from Thanksgiving? 2? Okay. My experience with this is that after Thanksgiving, people have checked out. Like, they've checked out. And so, all right, well, let's not officially move it yet, but let's start thinking like 80% that it's going to be 2 weeks from today.
If it's after, can I still make it up, like come into the tutoring hours?
If it's after, we can figure something out, as long as I know ahead of time. Okay.
For sure gone that week.
We'll decide for sure Thursday, all right? That way we know for sure. All right, today, all right, so what we did the last classes, we talked about, last 2 classes, we've talked about one-to-one functions, inverse functions, and how we check to see if something has an inverse, right? We did all that last class. All of that is to get us prepared for what we're about to talk about, which are exponential and logarithmic functions. So we're going to start with exponential functions. This is 6.3. And I want to get us going with this idea of exponential functions with an example, something visual. Yeah, I can use this. Okay. So we're gonna do a little visual demonstration here to get us thinking about what exponential functions are. All right? Up to this point in this class, when it comes to functions, the ones that we've studied are linear, quadratic, polynomial, rational. And if I give you any of those 4 functions, you should have some comfort level in terms of graphing them, right? Graphing a line, graphing a parabola, graphing a polynomial, right? That's the whole touch, bounce, multiplicity, and behavior, rational functions, lots of things, horizontal asymptote, vertical asymptote, x-intercepts, right? Test points. We should be able to do this. All of these have a certain place in the real world, right? Linear functions, parabolas, right? Polynomials, I've tried to show you some places where they appear in real life. So now we're going to talk about exponential functions, and we're going to see that these 4 are great, but they're not good at modeling what I'm about to show you, all right? So this is a rectangle, right? Everyone see this, right? Okay, so I'm going to make a good old-fashioned T-table, and we're going to play this little game. Over here, I'm going to put the number of folds that I have in this piece of paper. And over here, I'm going to put the number of rectangles that we see. All right? So right now, I have not folded this piece of paper, right? And do you see how many rectangles? 1, right? Okay, so no folds. One rectangle. Okay, now I'm going to fold it in half one time, right? And then I'll draw a little line across the crease so you can see it. How many rectangles do you see now? 2, right? It's fun, right? 1, 2. Okay, now I'm going to do it again. Fold it once, fold that in half. I'm going to open this up and we're going to see how many. How many rectangles do you think? 3? 4, right? 4. 2 folds, 4. All right, this is where things get a little interesting. I'm going to go again. So what do y'all think? 6, 8, 16. Let's see, can y'all tell? We have 4 across the top, and then we've got 2, right? 4 times 2 is 8. We have 8 rectangles. So 3 folds, 8. What do you think's coming next? 16 is what's going to happen next. I'm going to get to a point where it's going to be hard to fold. Come on. So 4 across the top, 4 down the side. Y'all see it? So 16. So what's the pattern that we see here? What's happening each time we go? It doubles, right? So we should expect to see 32 next, right? So if we do 5 folds, do you trust that it's 32? It is. All right. And have y'all ever heard of a show called Mythbusters? It's an old show. Yeah, there's a myth, I guess, that you can only fold a piece of paper a certain number of times, and then you can't fold past that anymore. And I think they got up to 13 on their.
A piece of paper like the size of a building.
Yeah, they took a paper. It's like real thin, like
Origami.
real thin paper, and it was like the size of a football field, a warehouse, and they folded it and they rolled over it with a steamroller. And then they folded it again and folded it again. I think they got up to 13. I think. It might have been 11. I'm not sure. Yes?
If you fold it like, 32 times, you can get to the moon or something?
Yeah, so the thing is, what's happening is each time this is doubling, right? So the question would be, let's say I tried to fold it 13 times. What would I get here? So the only way to do that right now is to first figure out what 6 is, right? And then 7, then 8, then 9, then 10, 11, 12, and then 13, then we could figure it out, right? But the question is there a function where this is the input and this is the output, right? Is there an actual function that I can find where I don't have to like complete the table all the way to 13 to figure out what happens at 13? Make sense? So what we have to realize is that since these all double each time, we're multiplying times 2 each time, right? Times 2 each time. We can say that all of these numbers should be powers of 2. For example, this first number is 2 to the first power, right? Or the second number. This one is 2 squared. This is 2 cubed. This is 2 to the 4th. This is 2 to the 5th, and so on and so forth, right? And so you can see that the power, right, is the input, right? This power is that input. Does that work for this one?
Yeah.
Is this 2 to the 0? Yes. Any number raised to the 0 is 1, other than 0. 0 to the 0 is undefined. But any non-zero number raised to the 0 power is 1. So this works, yeah? So what we need to figure out is what is 2 to the 13th power. And this is, I forgot, I sent that email last night saying I might be late today, and I didn't have office hours this morning. But I forgot to tell you to bring your calculator. So from here on out, make sure you're bringing your scientific calculators to class. We're going to use them. So get your calculator out. If you only have a phone, that's okay today. But you need to know how to do that on your calculator. 2 to the 13th power. So you should have a key on your calculator. A lot of you should have a key that looks like this. We call that the caret key. So that means raised, right? 2 to the 13th power. So go ahead. Who wants to give me that number? 2 to the 13th. What do you get? 8,192. 8,192. Okay? So here's the idea of the Mythbusters is that if you have a sheet of paper, right, think about it this way. If I don't fold it, right, if I don't fold it, this is how many rectangles I have, but isn't this also how thick it is, how many pages thick it is? Like this is 1 page thick, isn't it?
Yes.
If I fold it one time, it's now 2 pages thick, right? If I fold it twice, it's now, can you all tell? 1, 2, 3, 4. It's 4 pages thick, and so on and so forth, right? So if we could fold it 13 times, it would be 8,192 pages thick. Now think about like a standard textbook, like a textbook is, well, how about a ream of paper? You know what I'm talking about? When you get like a Office Depot or something, you get that package of paper. How many sheets of paper is in a ream?
Like 1,000. 500.
I thought it was like 200, no? 500?
250.
250? Yeah, it depends. You can get bigger reams, but I mean, if this is only like, let's say 300 pages and we've got 8,000, you're talking about, you know, pretty big stack, right? How is this paper, how can this piece of paper right here physically be this tall when the paper's only this big, right? Does that make sense? So that's why the Mythbusters got that real big sheet and folded it. But let's just keep going. What about, do you think it would be possible to fold it 20 times? Well, probably physically we couldn't do it, but how many rectangles would we have? Or I should say, how thick would it be? So 1 million, what is 1 million 3?
1,048,000.
48,000? 576. So now you're over 1 million pages thick. 1 million pages thick, or 1 million rectangles. See, this is growing very quickly, isn't it? So let's see, do we have a function? Do we have a function that does this? Well, the input is this number, right? That number's the input. What never changes in any of these is that number on the bottom, which we call the base. So 2 stays, and then this is, the x is up here, right? This right here is our first example of an exponential function. We call it exponential because the variable is in the exponent. If you go back and you think about linear, right? I'm going to give you an example of a linear function, f of x, 4x plus 1, quadratic, f of x, x squared minus 3x minus 4, polynomial, blah, 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 rational. In all of these examples of the 4 functions we've studied, where does the variable live? Down on the bottom, right? Not ever up in an exponent. And so since the variables here are down on the bottom, these are not exponential functions, right? That's our first example. Okay? Question?
Is it when you use like the log base?
That's coming next. So we're going to study exponential functions first, and then the natural question after we study them would be, do these have inverses? And they do, and those are the logarithmic functions. So the logarithmic function is the function that undoes this, but that's coming. That's later. Okay, so that's your first example. All right, let's do another example. Oh, you know what? This function right here models what's happening. This models what's happening with the rectangles and the folds, right? But this function does not have to be rectangles and folds. This can just be a regular old function, meaning we don't have to just plug in whole numbers. If you wanted to, like forget the rectangle, because I can't fold a piece of paper like 1.2 times, right? But I could plug 1.2 into this, couldn't I? You could do it on your calculator. So we'll investigate it more. We'll investigate what we can and what we can't plug in. Are there any domain restrictions? What's the range of this? We'll get to that, but I want to do one more example, maybe 2 more examples. This next example, again, is visual, and I can use a piece of paper. Let's take this same piece of paper, all right? And let's say that this piece of paper, just for the sake of making it simple, is 1 foot long. I mean, normally paper's 11 inches, but I'll just say this is 1 foot, okay? What I'm going to do is I'm going to make it, so this is a new problem, new demonstration here. This is going to be the number of cuts, and then this is going to be the length. All right, so what I'm going to do is I'm going to cut this. Right now I have not cut it, right? No cuts, and it's 1 foot long. And now what I'm going to do is I'm going to cut it right down the middle, okay? Perfect pair of scissors. I cut this down the middle. Now how long is it? 6 inches, or I'm going to keep everything in feet. So this is now 1/2 foot long. Got it? Now I'm going to cut it again, right down the middle. When I do that, how long is it? 1/2 of a half, right? I just took half and cut it in half. What's 1/2 of a half? 1/4. 2 cuts, 1/4. Do it again. 1/2 of a half of a half should be 1/8, right? That's 1/8 of a foot now. 3 cuts, 1/8. And I could keep doing this, right? Next cut would be what? 1/16. Do y'all see there's a similar pattern in this one than the other one? It's like flipped, yeah. So we get 4 here and we got 1/16. If I could continue doing this, if I could, theoretically, if we don't talk about atoms and things like that, in theory, would I ever run out of paper?
No.
Theoretically, no, right? Because I can keep taking half of half of half. I'm never going to get to 0, will I? In theory, I just keep getting half and then half. I remember, I think I was in 5th grade when my science teacher, she started at one end of the room and she said, okay, class, if I start here and I walk halfway across the room, right? And then I walk halfway again, and then half of that, and then half of that, and half of that, will I ever reach the other side? So again, in theory, no, right? You can always go half that distance, half that distance, half that distance. That's basically what's happening here. So the question here becomes, can you come up with a function that models this behavior? So what happens each time we take a step through here? We're multiplying by what number? Half, right? We're multiplying by a half. 1/2 times a half is a fourth. What's 1/4 times a half? That's an eighth. 1/8 times a half, 1/16. So a good candidate for the base of this exponential function is 1/2, and then I'm just raising that to the power x. And of course it works for this one, right? This is just 1/2 to the 0. This is 1/2 to the 1. This number is 1/2, right, squared. 1/2 times a half is 1/4. Got it? Okay, so I've given you 2 examples of exponential functions. I'll do one more, but I'll go quickly, all right? Do you all know what a Petri dish is?
Yes.
What's a Petri dish? So this is a biology thing, right? What's a Petri dish? It's a little plastic dish, or what is it?
It's a little like a little.
It's all like transparent plate where you
Transparent, small, almost nearly flat, transparent plate where you put like little stuff like that.
But what makes a Petri dish special? I mean, why is it? What makes a Petri dish like?
it has something for everything to grow on.
Okay, so it has this little like a gel on the bottom. Okay, but it's sterile. Okay, it's sterile, meaning that when you have a Petri dish, there's absolutely no bacteria or anything living in that dish, right? And so what you do is you go like take a Q-tip and you swab the handle of the door right there, you swab your cell phone, and you rub it into the Petri dish and you close it, and then you come back later and it's like, holy shit, and it's like all this stuff growing in there, right? And you're like, wow, that came from the door handle, right? So this example is going to be of just some theoretical bacteria. You know, bacteria, they're all bacteria are different, right? Did y'all hear about all the elephants that are dying in Africa? Did y'all hear about that? No. There's a bunch of elephants that have been dying in Africa, and they couldn't figure out why, and they finally figured out it was a bacteria or something like that. So, okay, so there's this. let's say that we have this bacteria, all right? I'm going to make this bacteria up. And here's what I'm going to tell you about this bacteria. This bacteria triples every 12 hours. So I have this particular bacteria, and what happens is the bacteria, this cell like splits and it becomes 3 bacteria. So it splits into 3. 1 becomes 3, and it only takes 12 hours for that to happen. Okay? My question is, how many bacteria this will be the first question. How many bacteria after, let's just say 2 days. And then second question, how many bacteria after 4 days? And then last question, 2 weeks. All right, so what?
Starting with 1?
We're starting with 1. Yeah, there's going to be a single bacteria. That'd be hard to do, to put 1 bacteria in there, but let's just, for the sake of doing it. So here's my visualization of what's happening. We have 1 bacteria at the very beginning, right? He's happy. He's got the whole petri dish to himself, right? There he is. And in terms of time, let me put time over here next to it. This is let me put it on the other side. How about that? Time over here. At time 0, right, there's the bacteria has been placed, right? Now, 12 hours later, right? 12 hours later, what would I have? I'm not answering these questions yet, okay? What would happen after 12? So this thing splits off into 3. And they're all pretty happy still, right? Now they've got some friends. All right.
Would there be 4 if you still have them?
So it depends on how we're saying this actually triples. What I mean by triples is that 1 becomes 3. Not 1 spawns 3 additional. Then you could say 1 becomes 4, right? So this is the way I want us to look at it, all right? Okay, what happens after 24 hours, right? This is time in hours. So how many will we have in 24 hours? 9, right? 9. Because this one triples. 1, 2, 3. This one triples. 1, 2, 3. This one triples. 1, 2, 3. See, we have 9, not 6. They're still pretty happy, I think. All right, let's see. Let's go 12 more hours. 36 hours. Now how many? Is it 18?
No.
What is it?
Oh, it'd be 27.
It's 27. 27. Because, well, here, let me put next to this. Here we had 1, right? Here we had 1. This is the number of bacteria. Okay, we had 1, and then we had 3, right? And then we had 9, and now we have 27?
Yep, yes.
0, 1, 1, 3, 2, 9, 3, 27. And what's happening each step? It's tripling, right? It's tripling. So when I get to, sorry, this should have been 12. Sorry, I messed this up. 12, 24, 36. So 48, we should have how many?
81.
81. We're tripling, right? We're tripling. With me?
Yep.
Okay. So because it's tripling, right? Because it's tripling each time, it looks like the function should be 3 raised to the x, right? But that's not going to work. Why is that not going to work?
You could set it, well, because 12 isn't gonna.
Yeah, because when I plug 0 into this, it works, right? This is 3 to the 0. That is correct, isn't it? But is this really 3 to the 12th power? No, right? What is it? 3 to the 1. This one is 3 squared, 3 cubed, right? 3 to the 4th. So what we need to do is we need to make an adjustment to our function. Pay attention to this because this is actually pretty important. I need to make an adjustment. When I plug in 12, I need to get 1. When I plug in 24, I need to get 2. When I plug in 36, I need to get 3. When I plug in 48, I need to get 4. How can I do that? I need to tweak something here.
You can make it x over 12.
Make it x over 12. Make this x divided by 12. And now, what happens when you plug in, let's try 0. What's 0 divided by 12? Still 0, right? 3 to the 0 is 1. Works. What happens when I plug in 12? 12 divided by 12 is 1. And that works, right? 24 divided by 12 is 2, and it works. See? So we have to tweak it, but it still is an exponential function. All right, this is an exponential function. But the base, right? The base is 3. So I've shown you now, what? How many examples? 3 examples. One of them was 2 to the x. One of them was 1/2 to the x. And now I've shown you this example, 3 to the x over 12, right? We have 3 examples so far. Now we haven't answered the questions, have we? Let's go ahead and answer them. After 2 days, can we figure out how many after 2 days? Well, 2 days is 48 hours, right? Because everything is in hours for us. 2 days is 48 hours. So that was 81, isn't it? 81. So the answer to this question right here is 81. Now, how about after 4 days? The thing about exponential functions is this. When you go from 2 days to 4 days, that doesn't just double, right? That's not what's happening. What we have to figure out is, what is this in terms of hours? So how many hours in 4 days? What is it? 96 hours in 4 days. Right, 4 times 24? 96 hours. So the question is, what happens when I do 96 hours? This is 4 days. Okay, plug it in, right? You got to plug it into this. Let me do that right here. 3 to the 96 divided by 12. What is it? 3 to the 8th? And what is that on your calculator? 6,000? 6,561? So you say 61?
Yeah.
Sorry, I'm hard of hearing today. Look at that. So look, yeah, after 2 days, right? After 2 days, you only have 81 bacteria. No big deal, right? 4 days later, you're up to 6,000. Right? So it's not doubling, right? You went from basically, in 2 days, you went from 1 to 81. Then 2 days later, it's a huge growth, right? And now let's try 2 weeks. 2 weeks is how many days? 14 days. 14 days. And then multiply that by 12, I mean, not 12, 24, because that's how many hours in a day. So what's that times 24 hours? 336. So we need 336 into this function. So we need to do 3 raised to the 336 over 12. What's 336 over 12? 28. And I don't know, how does your calculator handle that? 3 to the 28th.
22,876,000,000.
Is it giving you the dots or no? I mean, not the dots.
Scientific notation.
Is it giving you scientific notation? No?
876,790,000,000.
Yeah, so who's getting scientific notation? I'm going to write it both ways, all right? So when we put this in, any questions on what we're doing, trying to get this into our calculator? Okay, when you put that in your calculator, some calculators are just going to give you the number. Some of them are going to give you scientific notation. So no number, right? I mean, no. You have, yours is regular. Give me regular. Go ahead. Just list the numbers.
Just numbers?
Numbers.
2287679245496.
There we go. That's how many are there. Now, in scientific notation, who has scientific? What does it say?
Well, it technically should be 2.29.
2.29 times 10 to the 13th. Anyone have something that says E on theirs?
Yeah.
What does yours say?
.287679245.
And then what?
E,
E?
5, then E.
Oh, 5 and then E
13.
13. Okay. So all of these mean exactly the same thing. All right. Now this one includes every single digit correctly, right? This one rounds. So they round this, they say 228, they round that up to a 9, and then the times 10 to the 13 means you move this decimal place 13 places to the right, which would give you this, but see, they're neglecting all this. They're rounding it. Does that make sense to you? Yes? And then this one, same sort of thing, except the E means, this E means this. It's the same thing. E13 means move the decimal point 13 places to the right. That's a big number, right? What is that? This is millions, billions, trillions, right? What's the federal deficit right now?
It's in the trillions.
It's in the trillions, right? Y'all know what the federal deficit is?
It's 33 trillion.
It's 33? Really, is it? Bigger than that. $33 trillion is how much we what? I don't know. What's our debt? Like credit card debt? You mean it's something like credit card debt? Yes, that's exactly what it is. Right? What are the lessons hopefully you've been taught by people around you about finances, right? Don't borrow money. If you can't afford something, don't buy it. Don't borrow money, right? If you borrow money, you're going to have to pay it back plus interest. That's what credit cards are. That's what credit cards are, right? Don't do it. Yet, our government does exactly that, right? We spend more money than we bring in, and we borrow money from other countries. Like? Who's our biggest lender? China. China. So China's like our bank. And they say, okay, we'll give you more money. Trillions of dollars. How many people are there in the United States? What's the population of the U.S.? How many? 8 million, no. Come on, you got your phone. Someone look it up.
It's like 370 million or 400 million.
Let's go 400. You gonna look it up? No? Look at the population of the United States.
It's like between 3 and 450 million.
Roughly. I think it's about 400 million. We're going a little off topic here, but it's worth it.
Every person has 2.2 kilograms.
Do you still have this number up?
Yeah.
Okay, hang tight with it. You got it?
The service is horrible here.
Oh, no, nothing?
I can get
Let's
it.
go with 400 million. I think that's an overestimate. So can you please take this number and divide it by 400 million. That's 400 million. Take that and divide by 400 million. Tell me what you get.
57,000.
57,000.
191.
Close enough. $57,000. Basically, our federal deficit, we could clear our account and get us to a zero balance